Okay, so. The conduction. And electrical analogs. Okay. First of all, its current per unit of area. Okay. Area measured perpendicular gradient. We want to know that the flow is opposite to the direction of gradient for heat flow. Okay. Now, what is it for fluid flow? Is it in the direction or opposite the direction of the gradient?
Would be opposite.
Opposite. Yep. Because fluid flow, we're talking about pressure gradient. Okay. And pressure gradients in the direction in which pressure increases. And flows in the direction in which the pressure decreases, meaning you have less force on one end of the element than the other. Okay. And then we'll leave it for electrical gradient, because we don't know what an electrical gradient is, although I'll kind of tell you in a minute. We can do that easily. They'll say that's not yet specified. Electrical current. That last word's current, it kind of got slopped in there. Okay. So let's just demonstrate. Okay, so we know in lab, we've observed in lab, we've got this whole stack of metal plates. Okay, if we stack them up, then each plate, single plate, about that thick, fairly thin, about 1.3 millimeter thickness, I think. And I didn't put a micrometer on it yet, so I can't give you anything more accurate than that. Okay, but we take this stack and we set it on something hot, something that stays at a constant temperature. Okay, and that was a crock pot full of water with a big ceramic tile on top of it that had been heated up much earlier, like plugged in the night before. So it's maintaining constant, very, very nearly constant temperature. So we set these on top and leave them for a while. Okay. Actually, when we measured it, I think they've been sitting there overnight. So the top was at a constant temperature and the bottom was at a constant temperature. Okay. This temperature, of course, is higher than this temperature because the top was exposed to the air in the room. So it's like we went from maybe 110 degrees down here to 70 degrees up here. That would be a 40-degree difference. And the temperature gradient then would be 40 degrees divided by this distance. And this distance is, use the meter stick, about 3 centimeters. That's about 40 degrees per 3 centimeters, which comes down to 13.3, 13 1/3 degrees per centimeter. That's our temperature gradient. That causes heat to flow. And we did find that the temperatures of these things, as we measure them, gave us a very linear graph. Okay, so that's confirmation that we had a constant temperature gradient. Okay. We had a certain amount of heat flow here. Okay, the heat flow came out to, I think, something like, and we measured this by putting a metal cup essentially on top of this and measuring how much the temperature changed. Okay. The temperature of the water changed over several minutes. And it was a pretty rough estimate because we didn't have a real accurate thermometer. It's an accurate thermometer, but it's in, it's an alcohol thermometer. So we couldn't measure it. We couldn't read it all that accurately, but we estimated that we're getting about 50 joules per minute. Well, that's your heat current. Okay, 50 joules of heat per minute flowing from this end to this end. The current density is that 50 joules per minute, which comes down to what, 0.83 joules per second? Yeah, 0.083. Yeah. These plates are about 6 centimeters by almost 4 centimeters. So they have an area of about 20 square centimeters. Okay, give or take a couple. And what was probably a little over 20, the way it measured out. Okay. So in other words, cross-sectional area here is measured perpendicular to the heat flow. Heat flows this way, and these plates are perpendicular to the heat flow, or the heat flow is perpendicular to the plates. Okay, and that's pretty intuitively obvious. We can set up the diffusion equation and solve it with a partial differential equation, and we're not doing that in a simply calculus 1 based physics course. Even though most of the class, I think all the class, has had differential equations, you still didn't do that much with partial differential equations. That's a whole different ballgame. So we can't really prove that mathematically, but believe me, it works. Okay. Okay, so we have that heat flow. Now we're ignoring the fact that we're losing a little bit of heat from the sides of this thing. Mainly we're ignoring that because we had this thing insulated by styrofoam all the way, about a ½ inch of styrofoam. It's not going to lose much to start with. It's mostly going to be from the upper surface, but it'll be appreciable. But if we put the styrofoam around it, we pretty much ensure the linearity of our graph, temperature versus position, and everything else. Okay, well, that's a lot of background, but those are the things we think about here. So what's the current density? Well, if the current is, we'll say 50 joules per minute, okay, or about 0.83 joules per second, if you like. But well, 50 joules per minute is easy to remember. Then what's the current density? Well, you can divide that by the area of this thing. And you probably use SI units or something very compatible with SI units as opposed to square inches or square miles or whatever. Okay. So we'd probably divide by 20 square centimeters. That would give us a current density, right? So there's our first example. Zero point 0.5 joules per minute centimeter squared. Now, if we wanted the current through something that was, let's say, 30 centimeters by 30 centimeters, roughly a square foot, in other words, we'd have 900 square centimeters. So if we had 1 foot tiles stacked, same thickness, same number, or just a bar or a plate, a foot by a foot and a little over an inch thick, 3 centimeters. Okay. First thing, that'd be pretty heavy, but we could lift it without straining. But it would have quite a bit of weight in steel. More than you'd expect, unless you're used to handling steel. Okay. That'd be 900 square centimeters. All we have to do is multiply this current density by 900 square centimeters. Okay. Well, for a plate with the same thickness and same temperature gradient, the current would be the current density times area, right? I could write out the word current density times area. I'm not going to take time to write out all the words. Okay, that's really badly written because I'm writing fast and on the board. That's your 2.5 joules per minute centimeter squared times 900 centimeters squared. Centimeter by the centimeter will get joules per minute. And that's going to be, I think, 2,250 joules per minute. Okay, makes sense? It's just simple. The geometry is very simple, and the ideas are very simple. The formulas, as formulas can often be, can be a little confusing until you understand what they're saying, and then the formulas are pretty simple. So, got a question? Hang on. Okay, interesting connection. Let's say you had a steel wall with the same temperature gradient. And let's just say, okay, here's a steel wall. let's say you had a thickness of 2 meters. I don't know that anybody even makes 2 meter thick steel walls. That's kind of overkill. Okay. And that would withstand a nuclear explosion pretty close. But you probably wouldn't want to put your hand on the inside of the wall. Might roast you. But anyhow, thickness 2 meters. So what would the temperatures have to be? How much temperature difference would you have to have? Thirteen Kelvin per centimeter, okay? So can you figure out what the temperature difference would be? Well, I'll just tell you because it's really obvious. If you got 13 Kelvin per centimeter, thickness of 2 meters, that's 200 centimeters. Okay. So that's not, still won't melt at that temperature. I don't think. I don't melt a lot of steel. 500 Celsius will melt lead, I'm pretty sure. Used to melt that in a tin spoon over a candle flame. You can't do that with a steel spoon over a candle flame. The steel spoon will absorb too much of the heat and it won't melt the lead. Tin spoon, thin tin spoon doesn't. That has to do with heat capacities and stuff. It's kind of interesting. Okay, so anyhow, you'd have to have 2600 K, right? Difference between inside and outside. So if your inside is 300, the outside would have to be 2900 Kelvin. And that might, that'll melt a lot of metal, I think. Again, I don't have a lot of hands-on experience with those temperatures, so I don't have a good sense of it. I have to look at a tape. And you can take your phone and look that up in 10 seconds. Okay. Melting point of steel, melting point of metals. All right. So anyhow, that's kind of a conduction model. Now there's more to it. And I'll probably say more about it after we take a look at electrical conduction. But now let's say I want to run electric current through here. So there are my plates. I want to stand up. And I've got a couple of wires here. And I've got a 1.5 volt battery here that looks kind of shot. It's probably dead. But if it wasn't, we could easily put one end of the lead on each terminal and the other end of the lead of each lead on one of the surfaces, probably blocking the camera. I've got a really stiff neck, so I can't turn around and see if it's working or not. Let's see. If I put this here. I don't know if we even see that. That should be visible on the screen. Yeah. Okay, we got these things. We've got a battery, we've got some leads. We can attach the battery, one terminal here, one terminal here. Then we'd have 1.5 volts. Okay, 1.5 volts across here, across 3 centimeters. Well, what's the voltage gradient? Call that the potential gradient. It'd be 1.5 volts divided by 3 centimeters, which is 0.5 volt per centimeter. Okay, so in this case, our gradient wouldn't be I haven't even mentioned the temperature gradient here. I mentioned it. I said, from 70 to 110 degrees, right? So That's 13 kelvin per centimeter, right? And I did have that in here somewhere, yeah, 1300 kelvin per centimeter. Okay, the analogy here would be now voltage gradient in 1.5 volts over 3 centimeters. 0.5 volts per centimeter. Which could be written as 50 volts per meter, because meters 100 centimeters, you have 100 times as many volts over meter as you would have over a centimeter, right? The 50 volts per meter is your potential gradient. That's for the grid. It says potential gradient. Okay. This turns out to be your electrical field. Now, we're not going to develop that yet. We have to develop that and start with Coulomb's law and do a bunch of stuff. But we are going to look next at current flow. Now, how much current flows through there? Well, if we did the same experiment with the same inner and outer temperature using aluminum plates, we get a different result. Okay, that's because aluminum has a different thermal conductivity than steel. Let's just make another analogy here. More plates of the same dimension. Al for aluminum. Yep, E for iron, because that's basically what the steel is. The heat current would no longer be 50 joules per minute, which equals approximately 0.83 joules per second. To different conductivity. Y'all could take your phones and look up the thermal conductivity of iron, look up the thermal conductivity of aluminum, get the ratio, multiply that ratio by the 50 joules per minute that we're pretending is the heat current, okay? And you could get the heat current if it was aluminum. So we got this thing called conductivity. And I'm pretty sure that steel is more conductive than aluminum. I haven't actually ever measured that. I had a stack of aluminum plates, but that That's an expense we're not going to go to. We could actually measure it though, okay? First place, it's hard to get aluminum plates small enough to do this experiment. Second place, have a pretty limited budget, okay? But it would be possible to do. So you get this idea of conductivity. The greater the conductivity for a given geometry, the greater the flow, okay? Well, voltage or potential gradient the current density be determined by electrical conductivity. Well, given that these plates are steel, let's just call them iron for right now. We'll be pretty close. Steel has some other elements in it. Okay. When I worked in the labs, you know, your nickel, chromium, molybdenum, etc. Okay, bunch of stuff. And I didn't design anything. I just went out and ground up samples from chemistry. Yeah. And then filled out some forms. So I wasn't really doing a lot of science, but I got to see a lot. Okay, so if this is steel and these things are in good thermal contact, which they probably wouldn't be because of the coating on these things, okay? We know the area, we know the thickness, we've calculated the temperature gradient due to just a single 1.5 volt battery. So we can figure out how much current should flow through that. And we can measure that. Now it gets a little complicated because current also has to flow through the battery. And that sucks out some of your potential gradient. Okay. So you don't have the full potential gradient. But we could measure potential here and here with a meter. Just put a lead here and a lead here, and we can figure out what the actual potential gradient is. And then we could put an ammeter on it, just put the ammeter in series with the circuit, and get the current. Okay, so we could really verify this nicely. The other neat thing is, if I just apply the source of heat at a point here, or in a very small area, like, you know, the tip of one of these leads, okay, then I'm not going to have a uniform temperature across it. Okay, if I do it with the voltage source, I am going to have constant voltage across here and a constant voltage across here. So there are places where the analogy between thermal and electrical conductivity is thermal, like this is electrical. Okay. The analogy breaks down, but it holds in a lot of ways. And having had our hands on this, I think it's going to be useful to build these analogies. And your next assignment on the transition problems is going to be one that we deal with conductivity, which is why I'm talking about it today. Plus, it happens to be what you're kind of interested in. Now, I'm not going to write down a lot of stuff, but if you have a flow of fluids, okay, you have, again, good analogies here, okay? You have, instead of thermal difference or a potential electrical potential difference, you have a pressure difference. And that's what drives fluid flow. And fluid flow is measured in the flow per unit of area perpendicular to the gradient. Okay, fluid flows in the direction opposite to the direction of the pressure gradient. And there is a flow density. It's just the flow per unit of area in whatever pipe or channel or whatever the fluid is flowing in. And fluid flow gets a little bit weird, a little bit complicated. I'm actually infinitely complicated. If the fluid is flowing fast enough, it doesn't have to be all that fast, so you start getting turbulence because this model breaks down if you have turbulence. And we're not going to deal with that. It's an energy conservation thing. You lose more energy if you got turbulence. And if you can think it through in terms of energy, then, you know, it's some civil engineers worry about a lot. Okay. Okay. So I want to talk now about wave propagation in a string, or in the case of what we measured, the rubber band chain, which I find kind of fascinating. Okay. Now, you know this, presumably, having been through the transition set on waves. So I'm going to assume a lot of stuff. Okay. The propagation speed, as you should know, is v equals square root of t over mu. Mu being mass per unit length. Okay. Now, the rubber band chain, both t and mu depend on the length. So this is not a simple, trivial relationship. For a string that doesn't stretch a whole lot, or for a wire, or whatever, the mass per unit length is pretty much assumed to be constant. Not the case here. So the frequency of a given harmonic. Okay, so what that abbreviation means? Node, antinode, node, antinode, node, antinode. Introductory problem sets talk a lot about node, antinode distances. And I kind of think they might use this type of thing, but I'm not sure. I didn't think to look. Okay. But this would be the rubber band chain that has 1, 2, 3 antinodes in the middle. That means 3 peaks. It does. it does this, and then it does this, then it does this. Okay, you saw that, you experienced it. Well, the frequency depends on the length as well as the tension. Okay, now. I need proportionality constant. And I think I can get away with using K. Times L minus L naught. For L naught is the length of the thing when you just got enough tension to straighten out the rubber bands. Okay. And L is the length, of course, you know, as you pulled the thing back further, you felt more tension, and you saw the pulses travel down and back more frequently, and the frequency of your harmonics went up. Okay. So if the tension is K times L minus L naught, and mu naught equals M over L naught, and mu of L equals M over L. Then how does the velocity change as a function of two variables, tension and length? Well, V is a function of length. Tension is a function of length. And your denominator here is M over L. Mass per unit length, where length is now variable. That's as opposed to just tension over mu naught, which is what you'd have if the length wasn't changing. But the length changed by, 5 or 10%, and that changed the tension fairly significant. Now, tension really is not a linear function of length. Okay. First semester, we measured tension versus length by suspending masses from a chain of rubber bands, same kind of rubber bands that we were using. Okay. And if you have a good notebook, lab notebook, which I don't think it would have, but if you have a really good lab notebook, you go back and see how the tension changes with length and extrapolate that to this longer rubber band, roughly 15 meters. No, it wasn't that long, 10 meters. It varied from 10 up to maybe 12 meters. Okay. if you do a graph, tension versus length, presumably the graph is linear, approximately. Okay, really? Instead of linear, it's more like that could be the third one. Maybe something like that. It stays pretty close to linear, and if we assume the linear function, we're pretty close in everything that we want to measure, everything we want to predict. There's not a really good function that models this, but you probably use something like a Taylor polynomial. Okay, polynomial that has not just the first power of L, but second and third powers of that. We're not going to worry about that. I'm just saying, if you're really doing this with some kind of a material or whatever, linear approximation is often a good one. We use it a whole lot if you don't have a lot of variation. Okay. Anyhow, up here, we'll assume linear. So that would equal so we have a velocity function that looks like this. Now, the frequency is going to depend on the velocity and the length. Okay. A lot of times we use C for the speed of a wave. I'm not even sure I remember what your text uses. Different texts will use, some will use V, some will use C. Okay. Some reserve C for the speed of light and use V or maybe even another symbol. Okay. The thing we want to get into that I'm going to pose a question on, I want you to think about is that relationship. Okay. It comes down to understanding the node antinode configuration and how that, along with the propagation speed, gives you the frequency or period of the wave, depending which one you want. And mathematical description and stuff like that, all of which is there, I think, in the introductory problem set. So I'm going to be posing a problem. Okay? I just wanted to kind of frame this problem. I think maybe I wasn't completely on the screen when I did that. Okay. But the neat thing about this, it's a very neat idea. There's a lot of substance to it. Okay. You have this relationship, which you know from the introductory problem sets. We assume the tension is a linear function of length, and that tension is zero when you're at the minimum length. That's the length at which tension decreases. Reducing the tension, reducing the tension, reducing the tension. At some point, tension is going to reduce to zero at your initial length. Then again, your mass density depends on the length, which is not constant. So it's not constant anymore as it is problems in the transition set. Then you get into a relationship like this, then you got to worry about the frequency of these waves, but the connections are all pretty simple and straightforward. The derivative of this function with respect to L becomes important. Okay. It tells you the rate at which velocity, the propagation velocity changes with respect to how far back you pull. And there's a differential in there that can be useful. So we'll develop not an excruciatingly difficult model like the one we used for the miracle of a penny in the cup. Okay. But you want to be very familiar with all aspects of the transition set of waves. Another problem to look at is what we looked at last time, the model for the model engine. Okay, the model versus the model. So what we want to do is we want to say, given B naught the word for whether the gas is diatomic or monatomic, T naught H. Okay, T naught's your initial temperature, B naught's your initial volume. H is the distance to which you're going to raise the water. We again have a diagram. We're only looking at this much of the diagram, but you know, we have something like this. We have a cycle. Okay. We're only going to look at this part of the cycle. So here we have initial pressure. Here we have a case, we got T naught, B naught, P naught. And then we have T1, B1, P1, but P1 equals P naught, doesn't it? What's B1 equals P naught. Pressure versus volume. On a vertical, volume stays the same. And your pressure stays the same. If we know H, we know what this pressure has to be. If we know what this pressure has to be, then, well, we have all this. If we have H, then we know how much pressure we're going to need here. The volume is not going to change, so that we know what the temperature is going to be, right? So I can say H determines P1. Volume stays the same, so we can determine T1. Since we know T naught, P naught, T1, we can determine T1. Just by the gas laws, that's trivial. Okay. And QM. That's the heat that goes into the gas. If we also know T2, which is the temperature to which we can raise, well, the temperature we can achieve, the high temperature we can achieve. We're going to say T naught equals T sub C, T2 equals T sub H. So assume the temperature, cold temperature, the low the starting temperature is equal to the temperature of the cold reservoir, T2 to the temperature of the hot reservoir. It's not really true for the system that we can do because our hot reservoirs may be at 160 Celsius, 160 Fahrenheit, 50 some Celsius, 60. We can't really totally immerse the thing and get the temperature inside up to that temperature. But let's just assume we could. Let's assume we know what the high temperature, the achievable high temperature inside is going to be. We would have difficulty measuring that. We'd have to insert something sealed, through a thermal probe, sealed through the cap of the bottle. And I've tried to do that before. I haven't been real successful. Again, budgetary considerations. If I had a probe, I could permanently insert that way, we could do it. Okay. So my point is, we're looking at this. T2 is then TH. We know T2. T2 equals P1. T2 is TH. Allows us to easily find P2, right? Because we know everything but V2. So we can use the gas law to find V2. And of course, implicitly, the gas is confined. So in the PV equals nRT, N stays the same throughout. And we can find our change in potential energy, or delta U. Okay. So what I'm going to ask you to do, and I'll flesh it out a little bit, I'm going to ask you to come up with the formulas in terms of T naught and TH. And these quantities here, a formula for the change in potential energy. And this QN, I'm gonna call this QN 0, 1. That means QN from state 0 to state 1. And then QN from state 1 to state 2. And in both cases, that's going to just depend on the specific heat of the gas, molar specific heat, which is R/2 per degree of freedom. We talked about that last time, so might want to review that. I'll probably at least give you a good hint now. Okay, just want to get the mathematical relationships, no numbers, just in terms of symbols. In terms of these symbols here, the other symbols. What's delta PE? What's the total QN? Okay, as a function of height. Because if you change the height, you got to go to bigger pressure here. Then you got less heat to heat it up, so you're not going to be able to change the volume as much. Does that all make sense? Should. At this stage. But of course, questions arrive, I can at least give you more hints. So that's what we want to do with that. Pause for a minute, get my thoughts together. Okay, here's a quick rundown of kinetic theory as it's covered in the transition part. First of all, got a single particle mass m, moving at velocity b, reflecting off the two ends of the tube. Okay, so the path delta P at the end has magnitude 2mv. Okay. If I multiply, and I didn't do this is a unit vector in the direction of your motion. So I'll just introduce that right now. That's just a simple thing. It makes this into a vector. And it's negative because your change in velocity is opposite to the direction of your velocity. Okay. Now that's something you should know for impulse, momentum, and from what we learned about momentum. It's got momentum mv. That's got momentum negative mv. mv minus negative mv is 2mv. Oh, but it'd be negative mv minus mv, which would be negative 2mv. Okay. And I guess I don't need that unit vector. That's negative 2mv, or negative mv minus mv equals negative 2mv. It's a little side note. That's your change in momentum. Okay, now if the tube has length L, then delta P at a given n takes place how frequently? Well, the average force is delta P over delta T. That's your impulse momentum theorem, which says that delta P is average force times delta T, which is a simple rearrangement. And it's negative 2mv divided by 2L over V. So that the magnitude of the average force is mv squared over L. Which is 1/2 kinetic energy over L. Now, all this is there in the transition states. It's all there in the explanations or pictures and everything. Pretty sure I haven't looked that closely at it since I wrote it 30 years ago. Okay. Actually, I have looked pretty closely at it, but I don't remember all the details. But I'm pretty sure I have a very good handle on what's in there. So if I do say something up here that isn't in there, you should recognize everything. Okay, whether you put it all together or not, you should get having recognized. And let me know if you don't recognize it. Okay. Pressure. We're just talking about the pressure in this end here. Area is A. So what's the average pressure? It's average force divided by the area. And that equals one half the kinetic energy over L divided by A is 1/2 kinetic energy divided by AL. Well, this is a uniform tube. So A times L is just the volume. So we got pressure, average pressure equals 1/2 KE over V. We're getting close to PV equals nRT. Because the kinetic energy of the molecules is what determines temperature. This is just directly related to temperature. Then you multiply both sides by V and you got PV. So I'm going to gloss over the fact that this is average pressure. If this thing's moving at the speed of a jet plane, which is typical for a particle in a gas, and this isn't too big of a distance, you're not going to know the difference between one collision and the next. You're probably not even going to be able to measure it, except you're going to detect a little bit of vibration. Okay? And there's a very neat thing I can do with a tile and a BB, but I don't see a tile. I see some BBs. I'll save it. But you just take a 4-inch tile in your hand, put a BB here, and you have these tabletops, which have very high coefficient of restitution. Okay, you drop a steel BB on the tabletop from this height, and it'll come back to about here. Okay, you maintain well over 90% of your momentum on collision. So what you do is you release the BB, and then you just lower the tile to the tabletop. Every time the BB hits the tile, it speeds up. So by the time you get the tile down about this high, the BB's just bouncing back and forth, and it's pretty neat. Okay, and I've actually played around with the idea of measuring that force It just would involve some pulleys and building a frame that we don't have the means to easily build. We'd probably take some of these steel beams and magnets and build something that would work for a while and then fly apart and kill somebody. So I don't want to do that. Okay. And I'm doing all kinds of construction on my deck. Probably I got myself together enough, get enough pieces of wood to build something like that. It would be cumbersome and interfere with classes and stuff. So, okay, anyhow. Take PV will some number times T. Quickly, if you don't have just one particle, you've got a whole bunch of particles. Okay? Like 78 trillion particles, which isn't a lot. Okay? But you got 78 trillion particles in here, and start them all with the same velocity at the same point. Well, let's start them all with the same velocity over some segment here. Some of them are going to hit and bounce off and hit others that are coming toward it, and pretty soon everything is mixed up in 3 dimensions. Okay? So now we only have a third of the pressure. Why? Because only the velocity in the direction perpendicular to this end of the tube is going to contribute to the pressure. Okay? You can work that out, and it's worked out in the introductory problem says it tells you exactly why. The total kinetic energy is 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. Okay? Or m is the total mass of all the particles. And it's equally partitioned between all 3 directions because there's no preferred direction. Once these things start colliding with each other, they can collide in random so that they come off in random directions. Okay? And within a couple of microseconds, everything is totally random. And you got 78 trillion of these. Yeah, sometimes you got a little more energy in the X, sometimes a little more in the Y, but the variance is really tiny over any finite, over any small time interval, nanosecond or greater. You're not going to have, well, all the difference is going to be insignificant. And if you have rotation, then even if these things aren't rotating when they start colliding, one end of that rotating molecule is going to get hit and the other isn't. It's going to start rotating. And then you've got 2 more degrees of freedom because each direction, each possible direction of rotation, only 2, because it doesn't rotate about its main axis, okay, takes the same amount of energy. Does that make sense? Well, that's kinetic theory in a nutshell. It gets a little more sophisticated than that. If you look at the example and the way they derive the whole thing in your text, it's much more difficult than this. There's things that are hard to imagine. But you look at a small unit of area on any container, and then how many molecules are going to hit it at what speed, in what direction. And you got to make some assumptions. It's somewhat more complicated. I'm keeping this simple because we're just doing a minimal bit of work on this. So we have more time for the electricity. Okay. So then you only get a third of the pressure. Well, you get PV is 3/2 your kinetic energy. Okay. And we don't have time to say what happens to M and R, but that comes out really easily. If you got big N particles, then you put a big N out here and do the kinetic energy per particle. This is your total kinetic energy right now. Okay. And then R is just the constant that connects the kinetic energy to temperature. And that's something you measure in the lab. And there's, in a nutshell, a good start to the kinetic theory of a single gas. You get partial pressures and all that stuff. And we unfortunately aren't going to be able to do that. It's not too hard to understand, though, if you have this basis. So this ought to give you a basis for thinking about pressure in a gas. And PV equals nRT. Okay, well, we're over time and sorry for keeping you, but